Hello. Sorry I can't be with you today. Hopefully you are having a good lesson, good day so far. So we're going to do P10 Lesson 5, which is momentum in your booklets. If you turn to that page and do the Do Now task, it's the same as on the board. There is one change. You'll notice on question 3, in red, I've changed this bit to from weight of 50 kilograms to has a mass of 50 kilograms, because as we all know, weight is measured in newtons for science and mass is in kilograms. That question was slightly wrong, so change it in your booklets, please. Please pause the video and I will show you the answers when you are done. You should now only be watching if you've all completed all 4 questions, so we can check the answers. First one, Newton's second law of motion is at F equals ma. Force equals the mass times the acceleration. Just need to write that down, don't need to write the whole thing down, just F equals ma is fine. And next one, 43 meters for the stopping distance. We've got the stopping distance is equal to the thinking distance, so how long he's driving, or how long the driver is driving before they realise they need to stop. They'll pass 11 meters sometimes, so the reaction time. And the braking distance is 32 meters, so when they put the brakes on, from when they apply the brakes to when they stop, add them together and we get the total stopping distance, which is 43 meters. Question 3 is the one we had to change. Calculate the weight of a person on the moon. It has a mass of 50 kilograms and the gravitational field strength on the moon is 1.6 newtons per kilogram. We get a weight of 80 newtons, and that's because weight is equal to our mass times the gravitational field strength. So we do 50 kilograms times 1.6, which gives us 80. Final one, looking at the total stopping distance when they go from 20 miles per hour to 80 miles per hour. Slightly trickier. It's 120 meters. That's because our thinking distance is directly proportional to the velocity. So as our velocity doubles, so does thinking distance. So our velocity has increased by 4, gone from 20 to 80. So our thinking distance will increase by a factor of 4 as well, or double 4 times. It will go from 6 to 24 meters. Our braking distance increases by a factor of 4 when the velocity doubles. So we're increasing twice as much. So we go from 20 miles an hour up to 80 miles an hour. Easiest way to do it, I'll go 20. And I'll double it to 40, so my braking distance will go 6 and times it by 4 up to 24, and then double it again to 80, my velocity from 40 to 80, so I'll double my braking distance from 24 up to 96 and add them together to get 120. We will do some more work on thinking and braking distance. I know it's a little bit confusing. So, this lesson is looking at momentum, and momentum is a vector quantity. That means it's got size and direction. So just like velocity or force, it has size and direction. And we can calculate the momentum of an object by using the following equation. Momentum equals mass times velocity. So mass we always measure in kilograms. Velocity we measure in meters per second. And therefore momentum, its units are kilogram meters per second. Notice it's kilogram meters per second, not kilograms per meter per second. It's just kilogram meters per second because we're multiplying these units together. Let's have a look at working one out. We need to calculate the momentum of a sprinter of mass 50 kilograms running at a velocity of 10 meters per second. Now I'm going to write my equation out. I'm going to use the Greek symbol rho, which looks a little bit like that, equals mass times velocity. That's my equation for momentum. I'm finding out my momentum. My mass is 50 kilograms. I've got that there. My velocity, got it here, is 10 meters per second. To work out my momentum, I'm going to times them together. So my momentum equals 50 kilograms times by 10 meters per second and that will give me 500 kilogram meters per second. That's the momentum of my sprinter. So we can rearrange that equation if we need to. If we need to find mass or velocity, we can just do a linear rearrangement of that. Not going to go through that with you. You should be able to do that. If you can't do it, we'll take it up with your maths teachers. And we'll go over it another time as well, so we know we can definitely do this. So, big part that's really, really key to this. This is where it gets slightly trickier. Got the conservation of momentum. And this is a law. We like these laws in science. And momentum can be transferred from one object to another. So if an object collides with another one, it will make that other one move as well, potentially, depending on how massive that object is. And the important part is that the momentum before a collision is the same as the momentum after the collision. I've got two boxes here. We're going to imagine they're on a surface of ice. And this box has a mass of 1 kilogram, and this box has a mass of 1 kilogram. I will say that this box is going to move at 10 meters per second. I'm going to have it going to the right. Its momentum is its mass times its velocity, which will give us 10 kilogram meters per second. It's going to collide with this other box that's also 1 kilogram. What do we think is going to happen? Well, let's have a look. The box moving at 10 meters a second, it collides, and the other one moves off as well. That box moved to the right at 10 meters per second. It had a momentum of 10 kilogram meters per second. So I know there was a bit of a delay there to show what was happening when they climbed off. There will be no delay in real life. But we see them just moving off. They'll collide and move off. Now that was an elastic collision where they both moved, where they collided and the other one moved off. There will be times when they'll both move off together, in which case the mass will have increased. There'll be times they've got different masses. We've got a lot of stuff going on that we'll think about. So we'll have a look at another one. Now this time, same situation, but I've got a larger box that I'm going to crash into. We'll keep this one as the same. I've got it as 1 kilogram meter per second, or 1 kilogram mass there, and it's going to go at 10 meters per second to the right. So its momentum equals 10 kilogram meters per second. Let's have a look at this box. This box is, we'll call it 4 kilograms. What is its velocity going to be? We don't know, but we can work it out. Because we know, as we've said before, and we've said momentum is conserved. So this momentum is 10 kilogram meters per second. We can bring it over here. And that is still 10 kilograms meters per second. It's still going to be the same. Now, as I said, we can do a linear rearrangement of that equation. So momentum equals mass times velocity. We'll rearrange it to find velocity. I'm going to make velocity the subject, and that will give me V equals my momentum over my mass. So my momentum is 10 kilogram meters per second divided by my mass, which is 4 kilograms. On my calculator, type in 10 divided by 4, and I should get 2.5 meters per second. Let's have a look and see if we're right. The first one moving at 10 meters a second collides, and there we've got the other one moving off slower at 2.5 meters per second. Now let's see what happens if they are moving towards each other. So they're going to come towards each other. So they've both got the same momentum. They're both moving this time. So we'll both say they've got a 1 kilogram mass, and our velocity has a magnitude of 10 meters per second. But for our one on the right, we're going to give it minus 10 meters per second because it's going in the opposite direction. If we work out the momentum, we times them together, so 1 kilogram times 10 meters per second gives us 10 kilogram meters per second. our momentum on this side will now give us 1 times minus 10, and that will give us minus 10 kilogram meters per second. If we now work out the total momentum that we've got at the end here, our total momentum equals 0, because 10 plus minus 10 is 0. Let's have a look what happens when they collide. They're coming in together, they collide, and they stop. They're equal masses and equal but opposite velocities. The momentums will be equal but opposite. There will be no further motion, because that momentum still needs to be conserved. Alternatively, they could both bounce off each other at the same way as well. They could then both bounce off at 10 meters per second as well, which is probably more likely to happen. But we'll still get a total momentum of 0, because they're both going to go off in opposite directions. So we're now going to have a look if one of those objects is larger than the other. So we'll still go with the 1 kilogram on this side, moving at 10 meters per second. And we'll still go with our one here with 4 kilograms, but we'll also say it's going to move at 10 meters per second. Momentum on this side is going to be 10 kilogram meters per second. Momentum on this side is 40 kilogram meters per second. Now our total momentum, sorry, that should be minus 40, shouldn't it? Well pointed out there. Our total momentum, we've got 10 kilogram meters per second to the right and minus 40 to the left. So our total momentum of this system, we have 30 kilogram meters per second to the left. That's what we're going to expect to see when they collide. We're going to see a general movement over to the left. So let's see what happens when they collide. They're coming in together, and there we've seen the smaller blue box has bounced off and gone back to the left again. And the red box has been made to stop. We can work out that velocity just by thinking, well, we've got a mass of 30 kilogram meters per second, and the mass or the momentum of 30 kilogram meters per second, and a velocity of mass of 1 kilogram. We could work out the velocity using our rearrangement there. So, final bit for this: the momentum at the start is 0. The momentum at the end must be 0 as well. Before we looked at going, we had momentum at the start, it's still momentum at the end. If there's 0, it still needs to stay at 0. We've got here a picture of a cannon. If you've ever seen any cannons being fired, mainly on films, you'll notice that when they get fired, the cannon is pushed backwards a bit. They will rock backwards. If any of you have ever, something you might have done, no, ignore it. But if you look at cannons, they will get fired backwards. That is because our ball is flying out. It has a high velocity, but a relatively low mass compared to the cannon. The momentum forward, so if we say the cannonball has a mass of 3 kilograms and the cannon has a mass of 300 kilograms, our momentum to the left, where the cannonball's going, and our momentum to the right, where the cannon's going to move, must make 0. Because this thing was stationary at the start, there was no momentum. There still needs to be no momentum at the end as well. So if we say the cannonball leaves at 100 meters per second, we can work out the momentum. So our momentum equals our mass times our velocity. Our momentum equals 3 times 100. Our momentum equals 300 kilogram meters per second. We need to get 300 kilogram meters per second in the opposite direction as well. So for our cannon, so that was our cannonball on this side. Our cannon, our momentum equals 300 kilogram meters per second. which equals our mass, which is 300 kilograms, times our velocity. Rearrange that to make velocity the subject, and we will get velocity is 300 kilogram meters per second divided by 300 kilograms. So our velocity will equal 1 meter per second to the right, the opposite direction to the cannonball, to conserve that momentum. You can now have a go at completing the questions in your booklet. The stretch and challenge ones are on the next page as well. Please do pause the video or presentation now, and then we can go through the answers. So you should now only be watching if you have completed all of the questions. Stretch and challenge ones are here as well. We'll now show you the answers. Pause the video or presentation to mark your answers. And there are the answers to the stretch and challenge as well. That last one, thinking about two objects colliding from opposite directions, making sure that the momentum at the end is equal to the momentum at the start. I hope the video has been useful. We will go over this stuff again when I'm back in with you in case you've struggled with it. I know it is harder doing it without me being there, but hopefully you've had a good lesson. Thanks very much. Take care. Bye-bye.